So we are looking for theory background that with pre-made molecular models, we go to observables and compare to experiment. And right now, yeah, here are some subjects from previous years. Either tomorrow and Wednesday, we will select subjects of presentations. So, and homework is wishful, but let's make it like optional extra credit. I just do not have time to focus on it. So, yep, this is an important map. So whatever we are doing is matching this map. So also, Amir and Anand, please admit if anyone comes, and if anyone has questions to ask, please raise your voice, because right now I have hidden your camera, and I'll try to speed up as much as possible. So yeah, here is sure. Oh, thank you. So here is a learning map that we are trying to cover. So I hope very much that you were watching pre-recordings and slides for missed lectures. Did you? It will be no reason to watch them after tomorrow. So they need it only now. I hope someone was watching them, and I'll try to review, but it will not damage your grades, but it may damage your understanding, because like I physically cannot squeeze all materials, and we need to come to the certain point. So what we have missed, what are the cornerstones? So I will personally cover basically only last two, but we need total 1, 2, 3, 4, 5, 6, 7 lectures to get through Hardy-Fock theory. Some smart people know how to put it in half a page in a textbook, but if we copy it from there, it doesn't guarantee understanding. So the Hardy-Fock theory and anything in so we are focusing on electronic structure. It means we assume that the ions are nailed down, and we solve only electronic problem. The main challenge in this problem is that electrons repel each other, they interact with each other. And in order to take it into account, there are several tricks. So the major problem is a cost of calculations. Those of you low and heavy who are in the physical chemistry course, we are doing a project where we have only one electron, and in most realistic systems there are like hundreds or thousands of electrons, and they repel each other, and it makes major complication. So in order to account for multiple electrons interacting to each other, one uses several concepts. Slater determinant with antisymmetry. There was a lecture that makes connection between spin degree of freedom, singlets, and Slater determinant. So it was mostly entertaining, lecture number 10. Then there is a concept of mean field. And in very brief, the idea is that the only way to get through with up-to-date computational facilities is to assume that we are focusing only on one electron, and the rest of electrons in the system are not independent players. They just create a smeared out homogeneous charge that affects our favorite beloved single electron. So mean field theory. Then there is a so-called variational theorem that mathematically gives us paradigm that there is a minimum, there is such arrangement of electrons in a molecule that minimizes total energy. So theorem doesn't solve, it just tells that the minimum exists mathematically, and that we must believe it. And then by combining Slater determinant thing and mean field theory, one gets to Coulomb and exchange parts of electron-electron interaction. So you see there is a little plus, little minus. So this, like what is number 14, lecture 14, the electron interaction is expected to have positive energy. Lola knows it more than anyone else, right? Positive. But if you have multiple electrons, there is a trick that makes contribution to electron interaction, which has negative part. So in some sense, in many electrons, there is a part of the energy that stabilizes, that brings them together. This is very strange and unnatural. I'll try to review it today. And it is called exchange. So both Coulomb and exchange are colloquial words for different parts of Coulomb interaction. If we are simple guys taking freshman physics, there is only one Coulomb. But if we are computational chemists, with electron interaction is composed of Coulomb and exchange. And it's my job to explain, or at least review. Then, if one combines this concept of mean field, Coulomb, and exchange, one is coming to Fock operator that acts on one electron. And when it is combined together with variational theorem, one comes to an algorithm how to find the total energy, how to find this electronic structure, and how to bring there the concept of molecular orbitals. So it is a very rough overview, and when we go through materials, you will be able to report it in a much better way. Here is the same diagram, just with ugly handwriting. I think the previous one was better. So a little review. Here is the equation that we are solving. And before I started, I noticed Amir, Anand, and Haley online. I hope maybe there are more people. I just do not see it. Please, please, please stop me if something goes too quick, if you have questions. We better sacrifice amount of material, but we get through understanding completely. But this today and tomorrow, I will not make this interview style because I need to rush through material if possible. So here is the equation that we are solving. So it is eigenstates of all electron wave function. And since we nailed down ions, there is electronic kinetic, electron repulsion, and electron nuclear attraction. The psi, the wave function, includes many electrons, and we know that from concept of separation of variables, right? It is always a goal to represent wave function of many variables as little wave functions, each of which depends on one variable. So when we decompose many electron wave functions on the product of one electron wave functions only, this comes to idea of Hartree. And this idea fails to describe molecules. When we come to Fock and Slater, they brought in that for electrons, many electron wave function must be constructed from product of single electron wave functions in a very specific way. This very specific way is called Slater determinant. I will go very quickly. If you would live a normal life, it would be one lecture only for Slater determinant. So this phi with index, whatever, 1, 2, 3, depending on electron, either 1, either 2, either 3, are 1 electron orbitals, and index of this R1, R2, R3 is number of electrons. So here we have first orbital occupied by electron number 1. Here next we have first orbital occupied by electron number 2, and so forth. So the rule of Slater is that we make a matrix where in one dimension we change index of orbital, and in another dimension we change index of electron. and then form a determinant of this matrix. And this determinant will have summations and subtractions of products in a specific way, which comes from determinant definition. And if we construct many electron wave functions according to this rule, then it will be correct wave function that reproduces what happens in real molecules. So instead of simple products, one needs to do Slater products or simply Slater determinant. What it does, it brings us anti-symmetry, and anti-symmetry is critically needed. Here is an overview of the mean field concept. So suppose we have a molecule with whatever, on this diagram there are 3 ions, positively charged ions. Suppose we completely ionize it, removed all electrons, right? And then we return, we just borrow all electrons, and then, okay, I want to return it back to a molecule. When I throw in the first electron, it will take an orbital that looks schematically as this red thing. So it will be maximal density near ions, right? Because ions are so attractive. But when I throw the second electron, the spaces near ions are already occupied. Second electron is not allowed to go there because first electron screens it out, it repels it. And what we talked today about screened electron, to have like 5 instead of 11, it can be related to this. So because of the screening, second, I don't know how to go back. The smart screen is much smarter than myself. So second electron will take on this red black orbital, which will have different shape, and so forth. So each next electron takes a different shape, right? And why? Because those electrons that we have submitted before create negative cloud that repels our last electron. And this collective activity of all electrons that have been already deposited to the molecule create an average, a mean field. And we need to deal with it. Mean field of all but 1 electrons. Okay. And this another concept. In previous years, we were playing in Wheel of Fortune, the game when one needs to guess the letters, but we need to guess the word expectation value. So suppose we do have Hamiltonian. Suppose we have multi-electron wave function, which is composed of products or Slater products. Let's say only two orbitals. If we put them as a Brian cat from left and right from the Hamiltonian, it will bring us the expectation value of energy corresponding to this orbital. Orbital here, orbital there. But what if we do partial expectation value? What if we make not all electrons from left and right, but only few of them? For example, here you have total wave function composed of the phi2, phi1, and on the left you have only phi2. Then the resulting object where we do perform partial expectation value. So it is neither operator nor a number. It is a hybrid object. And this hybrid object is needed when we want to focus on one electron. So if you do such operation, it will be operator in respect to our favorite beloved single electron, and it will be like something average in respect to all other electrons. Okay. So suppose we are speaking on the simplest example. Well, simplest example for this course. For other courses, it will be already complicated. Suppose we have something like diatomic hydrogen, which has 2 ions and two electrons. So we can perform. So this Hamiltonian will depend on kinetic energy of electrons interacting with ions, and then electron repulsion, subtraction of positions of electrons. So we can make an expectation value average over second electron. But then the resulting thing will still be an operator in respect to the first electron. Or oppositely, we can do an average in respect to the first electron, and then the resulting object will be an operator in respect to second electron. But if we see that those equations are very similar, basically identical. So, and this is one of the ideas of Hartree-Fock. We make an average of all but one electrons in respect to Hamiltonian, and then we get an effective, not in a sense that it is so beautiful, effective like it is in effect does the same job. So we make an operator which effectively acts same as many electron operator, but it is one electron operator and works only on one electron. It gives dramatically beautiful increment of the productivity, with just orders of magnitude quicker, even if you lose some precision. Yeah. Okay. Skip. I want to hear some confirmation that I do not lose connection to the whole class. Let me. It's not my. I fear to lose, but let me ask. Ah, Queenie, here is our veteran of the computational chemistry, and I see Hanmant and Venji are here, and I do not see myself. I think camera is replaced by just by a screen. Unfortunately, I wanted to be a star on this movie. Please confirm if what I was saying it makes sense a little bit. Like thumb up if everything is great, thumb down is if it is nonsense, and just wave hand is if you wish we'll had longer discussion. Wavy, I noticed one thumb up, one wavy. Amir, more. Anand, more or less. Venjan, more or less. Hanmant, no signal. Okay. I'm hiding the images and we'll go forward. So what this slide show and what I'm going to do, it is still a review. And today we are going through like crazy. We already passed like 1 or 1.5 lectures in the expedited way. Now, what I'm going to do, I'm doing the same thing as I announced. My phi1 is my primary interest that I want to work with. No, yeah, phi1 is my primary interest. Phi2, here in this example, it is only second electron, but in the big picture, it represents all but one electron, the rest of electrons that create mean field. And here I am practicing this partial expectation value. So I multiply my electronic Schrodinger equation by bra of the phi2 from left and right, here and there, these red things. And then I'm going to carefully look at each contribution from kinetic, from nuclear to electron, and from electron-electron term, just to see what happens. By the way, if I look on the right part, the E capital is eigenenergy, is a number, so we can move it through, it will commute, and phi2 times phi2 will just give 1. So if you look on it, it will be eigenvalue E times eigenfunction phi1. And here is this crazy operator acting on phi1. So it's still an eigenvalue problem, but now it is in respect only to one electron. If you look onto the first part, kinetic energy of the first electron averaged over the second electron is still, here it has orthonormality, and we get an kinetic energy of the first electron. So average over the second electron doesn't affect it. If you apply this average over the second electron to kinetic operator over the second electron, it gives expectation value of the second electron. So here operator, here is the number. Right now I'm going through technicalities. If you are not sure, you can just lean back and relax, because there will be much more important concepts. If you can follow, please do. If not, just take a 5 minutes break until next important concept. So do not use your full intellectual strength right now. So going to the next term, nuclear to electron attraction. So if it is like hydrogen atom, there are 2 ions and 2 electrons. Totally, as you know from homework 1, 4 terms in the electron nuclear part. First nucleus, first electron. Second nucleus, first electron. And we can label them accordingly. Now, if we find partial expectation value of these 4 terms in respect to second electron. So from first one, it doesn't depend on the second electron. So we'll get nothing is changing. We are doing absolutely the same as it was before. N1, E1 remains operator. If you look interaction of the second ion with the first electron, if we do an average over the second electron, it still remains V and 1 E1. It's still operator. But when we do for the second part, interaction of first and second ion with the second electron, we are getting expectation values of this interaction. Those are getting numbers. Why I'm doing this long exercise, which I believe is not possible to follow. Later on, I will subtract all numbers and come to like close shell nice equation. Okay, and the last term, electron-electron interaction, which is the main bad guy in this equation. So V E2 E1, if we do averaging over the second electron, it will stay a hybrid. So it will be expectation value in respect to second electron, but it will become an operator in respect to first electron. If you find it strange, it is normal. Okay. Now, if I plug everything back into this pseudo one electron Schrödinger equation, you'll see that there will be, if I just process it, where we started from, and here we ended from. So it will be without bracket. It is an operator, kinetic, electron nuclear, electron electron, in respect to electron 1. And this in brackets, those are numbers that can be just moved and added to the eigenenergy. So if I subtract these numbers from the eigenenergy, then it will be like energy tilde, right? And we can reformulate this thing. You see this little tilde here as an eigenvalue problem in order to find the eigenfunction of the first electron and eigenenergy of the first electron. What?
Why do we have the tilde?
Because we have subtracted all pure expectation values, like everything that which is not operatorial. Okay. So variational theorem. Let's keep the words. Okay. Whew. Wipe off everything from your memories, switch the gears, and come to a new concept. Suppose we do have total energy operator H. Suppose we do know the multi-electron wave function. By forming this bra and cat expectation value, you'll get just total energy. Just in case, if we did something wrong, if our wave function is not normalized, we can divide by normalization, psi to itself. It just makes sure that dimensions are okay. It can be here or it can be removed. It's just a precaution measure. So here is the main philosophical part of this variational theorem. So suppose we do know absolutely correct wave function for many electronic functions, absolutely correct electronic ground state, and we will call it psi naught. Suppose it is known. Now, if we assume that we vary, so the word variational comes from the word vary, we change this wave function by adding a little contribution, this delta psi, and we get a new wave function, which is slightly different from absolutely correct wave function. Again, this is philosophical concept to be able to later on formulate things that we do in mathematical language. So the question is, what would happen to total energy if we move from absolutely correct ground state wave function to slightly changed wave function? And I know that some people like math and equations, and some people hate math and equations. And there is also people who prefer to see everything visual. It's just different mindset. So here is my visual thing, which may be a little awkward, but it suppose we have a like ground state wave function, maybe like something like Gaussian, maybe multidimensional, and then we have little additions on a side. If we add it together, we will have like central part and little tails. So how does such change of the wave function modify the total energy? And the theorem tells that if we modify wave function slightly from the ideal ground state, that the energy will be increased. So here is our expectation value for absolute ground state. And here is our expectation value of Hamiltonian for the wave function that is slightly changed. So if we are deviating, if we vary in our wave function away from the ground state, the energy will be bigger, right? If wave function is not anymore a ground state wave function, it means the energy will increase. Make sense? So it's quite natural, but it is placed in the more rigorous formulation. And here is a 1, 2, 3, 4, 5 lines, which are really silly. I just do not tell it in public. I expose. I'm playing silly here. It's not that we should do it. It's a really bad and silly idea, but philosophically it may work. So let's hire a programmer and ask him to extensively use random number generator. Now let's compose a random wave function, which will, in each point of space, it will be a little bigger or a little lower, completely randomly. Then for a random wave function, we compute total energy and save it into Excel table. For this wave function, there will be such energy. And then we repeat many, many times. So we just create random wave function, compute total energy, and then we order this list and find the wave function that gives minimum of energy will be absolutely correct. So it's not practical way, but it gives us, based on the theorem, and we are not going to prove, we just take it as a concept. It gives that there should be an algorithmic way to browse in a space of wave functions and vary it until we find a minimum. And we can make it continuous. We make small change and then look whether it increase or decrease energy. And it makes it very much similar to the idea of geometry optimization. For geometry, we slightly changed positions and inspected whether it gives increase or decrease of energy. Here, we just change shape of the wave function and see whether it increase or decrease energy. I hope this, maybe let me bring the faces again. Okay, please confirm that this idea of variational theorem was more or less okay. Like thumb up for absolutely okay, wavy hand for more or less, and thumb down for you absolutely against it. More or less? What? More or less? Absolutely okay. Absolutely good. Venjan, I missed your reaction. Are you okay with variation? Thank you. Anand? Hanmant? Yeah, thank you much for confirming. I'm very happy. Okay, I'm hiding your faces and we'll go forward. Okay. I'm going to disclose a little bit of core idea of the Hartree-Fock. We will not get everything today, but right in the next 3 minutes, you will come very close to understanding how it works. I promise. So when we were optimizing geometry, we were varying positions, interatomic positions for all possible ions. Now we are coming to the idea that is for low and heavy. It is an equation that Lola was presenting today in class, the last equation or second last, that wave function can be represented in a basis as a through expansion coefficients, right? So in application to computational chemistry, so I'll slow down and discuss the notations. We do have many ions in a molecule. Position of each ion I is symbolized by uppercase R sub I. And if we want to build molecular orbital, a wave function of a single electron, we need to include summation of all ions. At each ion, we have atomic wave functions, which are like S, P, D, right? And they depend as on the distance between electron from the ion. So this atomic wave function is symbolized by letter chi. So it looks like X, but people call it chi because it's from Greek alphabet. So chi sub A. Under the letter A, A symbolizes like S, P, D, spin up, spin down, things like that. Okay. So by adding together all SPD orbitals on all possible ions, we create a basis to represent of atomic functions to represent a molecular orbital. So our molecular orbital, which means one electron wave function, is a summation of all atomic orbitals on all ions in the molecule with different weight coefficients, with different expansion coefficients C, with indices C, A, and J. So again, with indices, the index J is index of molecular orbital. And indices A stand for SPD, I stands for different ions. So the expansion coefficient CAJ tells how much molecular orbital number J is contributed by atomic orbital number A. And in this sense, we can replace images of molecular orbitals by set of numbers of these expansion coefficients. Basically, when in the lab you are doing this form check and cube gen, you are doing transition from this CA sub J towards molecular orbital that depends on position, because these C coefficients are much more compact. If you have like, let's say 10 or 100 orbitals at each ion, meaning all diffuse, all complicated things, and like 10 ions, it will be just 1,000 coefficients. And molecular orbital itself is a cube about 1 million data points. So these C coefficients are much more compact. So once again, chi sub A of R minus R capital I are atomic orbitals, R uppercase sub I positions of ions in the molecule, and C is expansion coefficients. So this were definition. Now here is the idea. Single electrons are sitting on molecular orbitals. Like on each orbital, there is like 1 or 2 electrons if we have different spins. The overall electronic wave function is composed as Slater product, Slater determinant of all occupied molecular orbitals, right? And now we need prepare. I believe I'm going to say something important. Now we need to combine this idea with variational theorem. So we can slightly vary these expansion coefficients and implement this change towards way to compute total energy until the total energy will be minimized. So our space where we browse is expansion coefficients. And our function that we need to minimize is the total energy of the multi-electron wave function. So we slightly change this relative proportions of all atomic orbitals. We slightly change this formulation of molecular orbitals, which affect how the total energy is computed. So total energy as function of this expansion coefficients is basically what we need to do practically in the Hartree-Fock theory. Make sense? Okay. Whew. If you are taking notes, please record it. I think it is absolutely most important idea for the whole month. And here, this idea is summarized once again. So we have kind of a stream from positions of ions that is input to our practical computation to atomic wave function, which we choose as a basis, to expansion coefficients, to molecular orbitals, to multi-electron wave functions, to total energy. And we need to minimize total energy. We cannot change. Well, the only thing we can change is expansion coefficients. Atomic orbitals, we select the basis. Positions of ions, we select the geometry. The way how they're converted is already written. The way how the multi-electronic wave function is given by Slater. The way how to total energy is also predefined. So to minimize energy, the only thing we can change is expansion coefficients. Okay. It's the same idea. So this procedure of improving expansion coefficients is done in the continuous way. We are not guessing it once and another time randomly. We start from some maybe wrong molecular orbitals. And we slowly browse by making small variations of this molecular orbital. So we do a steepest descent, same as we were doing for geometry optimization. We just browse in the space of expansion coefficients until we find a minimum. And it is called self-consistent procedure. Okay. So let me bring up faces once again, because I'm done with one concept. I hope you are okay, or more or less okay with it. Please, okay. Now, if you have questions, feel free to stop me and ask. If you don't, I will go forward with new concept. So we'll switch the gears. Excuse me, I'm talking too much and too loud today. So I'm hiding your faces, and here is where I'm going. So just take 10 seconds break. Remove everything from your brain and prepare to focus on a new concept, new aspect. It's like concentrating your muscles before making a jump. I was developing the slides when I was teaching this lecture at University of South Dakota, and I was telling, like, be proud, SD can be abbreviated as South Dakota. But no, it is Slater determinant. So let's focus on the expectation value of electron-electron interaction under assumption that our wave function is Slater determinant, not Hartree product that comes naturally from separation of variables, but it's specific Slater determinant. And we are rushing very quickly, but if you, Anand or Amir, would you please accept Amara? Yeah, thank you. Amara, thank you for joining. We are looking on Slater determinants in respect to electron-electron interaction. So, I'm just postponing for a few seconds, most important idea. If you do remember what is determinant and how to take it for matrices 2 by 2, right? So if you have matrix 2 by 2, it will be main diagonal minus subdiagonal. So if we compose Slater determinant matrix of the first and second orbital for the first and second electron, then on the main diagonal will be first electron on the first orbital, second electron in the second orbital, and on the off diagonal will be first electron in second orbital in the first orbital, and there will be minus between them. Make sense?
Yes.
And so it will be ket, and bra will be the same thing but with little stars. Okay, so our multi-electron Slater wave function, Slater determinant, is this bra and ket of this. There is no better terminology. People just call Slater determinant. So it's not a product; it's determinant because it's sum and subtraction of products. Now, if we need to find expectation value of electron-electron interaction, we put this 1 over subtraction R1 minus R2 in the middle, and you have bra and ket, and we integrate over position of first and second electron. So if we mathematically perform this operation, we will get a number, which will tell how strongly 2 electrons repel each other. Okay? So what I hope is shown on my next slides, or if it is not shown, I will write on the blackboard. I'm going to open brackets and get 4 terms, because here we have 2 terms from first Slater determinant and 2 terms from the second, right? If I open brackets, I will get 4 terms, right? This times this. It's very smart screen. So different combinations. And in these 4 terms, signs will be either plus or minus, which means it will be either attraction or repulsion. So it will be dramatically different physical interpretation of these terms. So it will be something really interesting and important. So it's not just mathematical playing. It will be something much, much deeper. So we start from Slater determinant. And I think, oh, okay. Just take this idea and again, relax a little bit. I know it's too many new ideas. I will have about 7 slides with entertainment. Well, mathematical entertainment or computational entertainment. If you are already tired, just relax and wait. I'll give you a signal when it will be important to memorize and think. So now is just decoration. So when I was going through the things myself in my whatever undergraduate studies, I hated it so much. It's so unnatural and so unpractical, too abstract. And it's much easier to think about more things that are simpler that one can touch practically. So how to visualize these things? So here, again, lean back and relax. It's only entertainment. Here I'm trying to visualize what would happen if I have one-dimensional box, same as Haley was presenting this morning, and I will try to put 2 electrons into one box. So I will put I can put first electron. So it's X going from like maybe 0 to pi. And first electron will be in the ground state, which means it will change from 0 maximum and then 0, just one hump. And then it will be 2-dimensional diagram because 2 electrons are independent. So although it is 1-dimensional box, there are 2 dimensions because 2 electrons may do different things. And the second electron may take the first excited state or state 2. So it will go to 0, positive, I'm going screening a long way, then negative, and then again 0. So first electron in ground, second in excited. Or it can be opposite. Second electron is in the ground state and first electron in the excited, in the orbital 2. And visually, it will be just nodal plane of this thing arranged along y or x. So 2 electrons in the one-dimensional box. Those are Hartree products. We know they will give wrong answers. It was proved like almost 100 years ago. Now, the concept of Slater determinant. It means we need to subtract these 2 Hartree products from each other. And we can visually subtract the things. And then we will just get a picture where instead of nodal plane coming vertical and horizontally, it will go along the diagonal line. So it is just visual illustration how the Slater determinant would look for the 2 electrons in one-dimensional box. So if we swap a sign in front of this thing, or if you replace everywhere second and first electron, it will be the same effect. So the main idea of the Slater determinant of this so-called anti-symmetric wave function, that if one swaps 2 electrons, wave function changes sign. So property of the anti-symmetry, and one can illustrate it. If I do not believe you are going to spend your time, but below there are some MATLAB codes which will make this little experiment. It's anti-symmetric wave function. Now another experiment. if we want to find expectation value of the Coulomb, so we put 1 over x1 minus x2, which is like divergent thing along main diagonal, right? So when x1 equals x2, it will be infinitely high or infinitely low on the main diagonal. So if you take this Coulomb operator and convolute it with the Hartree product, there will be an interesting observation. So on the main diagonal and Hartree product, this procedure will give the infinite answer. So if you try to find electron-electron interaction, sometimes on the main diagonal, the wave function is non-zero. And when non-zero meets the infinite value of operator, it immediately goes to not a number, which means infinity. So it's something strange. But if we place there the antisymmetrized wave function, it has zeros on the main diagonal. And if you convolute it with the electron-electron repulsion, we will get some small number, some reasonable number. So it's just qualitative demonstration that we do not get nonsense, that antisymmetrization saves us. Okay, end of fun demonstration. Now I'm going to open brackets. So if you were sleeping, please wake up. We do have another 7 minutes where I will try to make them really intense. So term number 1, main diagonal in bra, main diagonal in cat. First electron in first orbital, second in second, first in first, first in second. The sign is positive. The operator has absolute value, so it's also positive. So this first term corresponding to main diagonal will give a big positive number. So it will correspond to electron repulsion, right? And if we go further and look for cross term, where on the bra we have first electron in first orbital, second in second, but on the cat we have first electron in second orbital and second electron in first orbital. We inherit the minus sign. So this minus sign is inherited because of our antisymmetric Slater type wave function. And this minus, so everything else here is positive. So the total answer will be negative. So this is a term that contributes to total energy of interacting between two electrons. But it has negative term. Negative term in energy means it stabilizes. It brings us to a minimum, to stable that doesn't want to break on the pieces. And the previous term is positive. People call it Coulomb. The negative one, which is a really good one that makes our universe to be stable, not to break on pieces, is called exchange. Why? Because here we put first electron on the second orbital and second electron to the first orbital. We swap, we exchange electrons between orbitals. So this exchange energy contribution to electron-electron interaction has stabilizing feature, and this is why Hartree-Fock theory, although it is not ideal, it gives many errors, but in principle, qualitatively, it is correct, and it is accepted by community as a main cornerstone before going to any other theories. So it includes this main part of the nature, that there is an exchange. And when you go to next theories, when you do like hybrid DFT, it tells hybrid DFT includes Hartree-Fock exchange. Means it includes this stabilization energy. Okay. Let's see. What else we have? Okay. I know that we need to finish in 3 minutes because some of you have additional duties, but I'll try to go a little bit if as much as needed. And if any of you need to leave, feel free. In 3 minutes, I'll just finish the thought. So suppose we are going to play the same idea with a single electron. So we want to create an operator that acts only on one electron, right? Single electron operator. But we do want to keep this multi-electron feature where electron-electron interaction has positive and negative Coulomb and exchange parts. So there is a way to construct one electron partial operator that would take into account this Coulomb and exchange nature. So for Coulomb, we have all indices. I don't know what I did. All indices the same here and integrate over R2. And for exchange, there will be a swap. Where it is? Yeah. A swap of order of electrons. And these terms are included into one electron efficient Hamiltonian that we discussed at the very beginning of today's meeting. And it is what is used to create molecular orbitals, to compute molecular orbitals. So Coulomb and exchange are included into one electronic orbitals. So yeah, here, skip those are from the labs. Another review. Slater determinant. Okay, so let me bring up faces and make sure that if anyone would stay or you all need to leave. Let me check who needs to leave immediately, sharply at 5. Please show thumb up. No one. Who is okay to stay few minutes more? Show thumb up. Okay. Yeah. Thank you. Thank you. Okay. But give me a signal if I'm overusing your time. I realize it. Okay. So this face is Richard Feynman, who got Nobel Prize for quantum electrodynamics. He was projecting quantum theory into interactions of electrons and photons, basically what Amos was trying to bring to us today. And one of his major achievements that is recognized by people as his heritage, that Richard Feynman taught scientists how to draw pictures. Not like pictures of like cats and sun and humans, but how to convert complicated, very complicated equations into some very simple diagrams. And basically Feynman diagrams, it is a way to replace like 10 pages of equations with a couple of simple lines. And by using Feynman diagrams, one can get the answer like 100 times quicker. So it's a way to convert equations into diagrams and backwards. Basically, one converts equation into diagrams, do some things that are humans typically make errors in diagrammatic form, and then just after one gets a final answer, return it back into form of equations and numbers. And here is just from Wikipedia. Basically, in his protocol, again, this smart screen. So in his protocol, straight lines with arrows mean either electron or hole or positron. and wavy lines mean photon or phonon. So if we want to convert our Coulomb and exchange onto the language of Feynman diagrams, or is it possible to convert our Coulomb and exchange onto language of Feynman diagrams? Yes. So for Coulomb, I'm showing, if you do not see my image, I'm looking on the lower left of this of the screen, and I'm looking on the greenish line that has index phi1 and phi1 star. So this line corresponds to it goes to the circle, blue circle with index R1, and it means first electron is residing in the orbital phi1 before interaction, lower part, and after interaction, top part. Then there is a purple spring or purple wavy line, which corresponds Coulomb interaction, which is like Coulomb interaction in Feynman's world means like there is a stream of virtual photons that go forward and backwards and are responsible for this interaction. But there is a Coulomb interaction, 1 over absolute value of R1 minus R2. This wavy line ends in the blue point R2. And there are yellow highlighted things which are labeled as phi2, which means the second electron was residing in the orbital phi2 before interaction, and it is residing in the orbital phi2 after interaction. So this diagram corresponds to expression on the top left part of the screen. So each electron stays in its own orbital. There is an interaction, and there is a positive part of this Coulombic repulsion. Here, we can say that time goes from bottom to the top, and somewhere in the middle, they interact. So this is quite natural. Now, what if we have the swap, the exchange? I am, if you do not see the camera, I'm moving towards right half of this diagram. So now I'm pointing on the bottom right, on the green highlighted thing. So that ends in a circle with number 1. So electron number 1 originally stays in the orbital number 1, right? And then it interacts with electron number 2, which originally stays in orbital number 2. And time goes from bottom to the top. And after the interaction, we see that on my leftish side, I suddenly find that I observe orbital number 2. And on the rightish side, suddenly there is a orbital number 1. So just to make connection with our equation and wrap our mind around it, we can show like little wires go across each other without intersecting, right? How the highway entrance just goes a loop and do not intersect. So originally we have electron 1 in orbital 1, electron 2 in orbital 2. After interaction, we will have the electron 1 in orbital 2 and electron 2 in orbital 1, which corresponds to the swap, this exchange. So nothing new, we already discussed it. It will have minus sign and stabilization thing, but we need to wrap our mind around how to make an average around electron 2 and how to make it one electron orbital, one electron operator. Okay, so we need such operator that would act. So I'm pointing on the top line, which need a such operator, which I call J sub 2, that will act on the electron number 1. It means we need to perform an averaging over all possible positions of electron 2. So this integration over R2. When we do this integration over R2, this purple thing will mean that it will be something that acts on electron 1 and symbolizes by this operator J2. So this purple thing and this integration over R2 means that we just hide everything on the right side of the diagram and consider it as a black or whatever purple box, where electron 1 in orbital 1 hits this box and reflects from it. Okay, so all this structure of Coulomb interaction, this integration means it is a box where electron just bounces back. If we do the same trick for the exchange, it means that we swap the no, it's still Coulomb. I need one more. One slide more forward. Yes. So the letter K exchange, we swap order here, we integrate over R2, but in spite of this operation, we suddenly swap the wave function on which we act, just magically swap this wave function phi2 in R1 with phi1 in R1. And it means that the electron we started with just disappears in this wall and the new electron comes out. It's a little crazy, but it corresponds to diagrammatic representation of this one electron operators which we need for the Hartree-Fock theory.
It doesn't bounce back, it goes inside.
It goes in and something else comes out, right? Like it goes to this pool. And I was just trying to illustrate it with MATLAB, but no time for it. Now, if you ever, I'm very close to finishing, maybe just one or two slides. So, if you ever going to read the literature about derivations of new computational theories or serious textbooks, I'm going to recommend only simple, but if you go to real advanced books, people use different ways of this electron-electron interaction again and again in different order. And people are very tired even to write diagrams or write equations. So they try to create shorthand notations. And this typical integral, where like here, chi is atomic functions with set of indices R, S, T, U. R and S for first electron, T and U for second electron. So people abbreviate it in the form as two round brackets with one vertical line, and then the indices for two indices for first electron, two indices for the second. By swapping orders of these indices, one can represent either Coulomb or exchange. We do not need it for the class. It's just so that when you see this abbreviation in the literature, you do not get scared and you know where to find the definition. For example, if one has RRTT or 1122, it will be Coulomb. If one has RTTR or 1221, it will correspond to exchange. Okay. I think it is more than enough, even if you have something left. I'll go to this thing tomorrow. Yes, thank you for investing your time. Let me bring the faces back. So if there is no camera, I'm just showing crossed hands, symbolizing that the meeting is over. Thank you much for investing your time. If there are any questions.